The contents present in this Unit 4 are operating system basics, types of operating systems, tasks, process and threads, multiprocessing and multitasking, task scheduling. In fact, we have discussed about two types of embedded firmware designs, the Superloop model and RTOS-based model in the previous presentation in Unit 3. Superloop model follows general task-by-task execution that follows foreground and background systems. That Superloop model is applicable for small systems for low complexity. An application consists of an infinite loop of desired operations. As an example, traffic light signals can come under Superloop model. Interrupts will be handled in the background, whereas asynchronous events will be handled in the foreground. The critical operations must be performed by the ISRs to ensure the timing correctness. ISRs tend to take longer than they should. Task level response, that is, information for a background module, is not proceed until the module gets its turn. These are few drawbacks related to Superloop model. Moreover, execution time of typical code is not constant. Based on the type of code, execution will happen. If a code is modified, timing of the loop also affected. Most of the time, high-volume microcontroller-based applications are foreground and background systems. As an example, microwave ovens, telephones, toys. The other shortcomings of Superloop model are execution of task is sequential. If you have n number of tasks, task 1 to task n execution is sequential. Each task has its own timing and other task has to wait till the first task or the previous task will be completed. And hence task execution is non-real time. If number of tasks increases, the time interval at which task gets served also increases. If any task wait for any external event, IO device uses or any other resource allocation, the task will be pushed into wait state. Few more shortcomings of Superloop model are priority cannot be modified. At the design phase, what are the priorities given to the tasks? With that, the execution happens. These are suitable for the systems where response time is not a critical issue. As an example, toys, video gaming. Hence, where RTOS is essential is to be observed. Systems with time critical response is observed with RTOS. Time critical response is present in the systems where flight control systems, airbag control, anti-locking brake system, etc. Any delay in the response may lead to catastrophic error. What are additional jobs that an OS should do under RTOS? The additional responses are assigning priorities to the tasks, allocating CPU time to the highest priority task to execute, dynamically change priorities if required on demand base, scheduling task execution based on their priorities, switching to execution of task when a task is waiting for an external event or any other resource. There are two types of systems, that is hard and soft real-time systems. Hard real-time system, in which failure to meet deadlines is fatal. As an example, flight control system. The other one is soft real-time system. Late completion of jobs is undesirable but not fatal. System performance degrades as more and more jobs miss deadlines. As an example, online database. Most real-time systems are embedded. Embedded system is a computer built into a system but not seen by users as a big computer. Users as being a computer. Examples: fax machines, copiers, printers, scanners, routers, robots. Here is a question: why is a desktop OS not suited for embedded systems? The major drawbacks with desktop OS are: monolithic kernel is not modular, where monolithic kernel is present in desktop OS. They are not modular, fault tolerant, configurable, and not modifiable. They take too much memory space. It is often too resource hungry in terms of computation time. Not designed for mission critical applications. Timing uncertainty also large. Monolithic kernel. This manages the system resources between application and hardware of the system. The user services and kernel services are implemented under same address space. This increases the size of the kernel, further increases the size of the operating system. General purpose OSs involved with monolithic kernel. Microkernel. Microkernel, being a kernel, manages all system resources. But in a microkernel, the user services and kernel services are implemented in different address space. That is a major difference between micro and monolithic kernel. The user services are kept in user address space and kernel services are kept in kernel address space. This reduces the size of the kernel and further reduces the size of operating system. Monolithic kernel used in GPUs, whereas microkernel used in embedded RTOSs. These are the differences between microkernel and monolithic kernel. As we are seeing this, microkernel hardware is common in both micro or monolithic kernels, whereas the entire kernel space is reduced in the case of microkernel, that is basic IPS, virtual memory, scheduling. Then in the user space, application IPS, Unix server, device driver, file servers. These are pushed into user space such that the space per kernel is reduced in microkernel, whereas application space is common in both the kernels. In monolithic kernel, that IPC file system, VFS virtual file system, scheduler, device driver, everything are pushed into kernel space. As the kernel space is large, it is not suitable for embedded designs. These are differences between micro and monolithic kernels. In microkernel, user services and kernel services are kept in separate address space, whereas in monolithic kernel, they are kept in same address space. Microkernels are small in size, whereas monolithic kernels are larger in size. Microkernels are slow in execution, whereas monolithic kernels are fast in execution as everything is present in the kernel space. Microkernels are easily extendable, whereas monolithic kernels are hard to extend because they have included with lot of utilities inside the kernel. If a service crashes, it does not affect working with microkernel. Whereas in the case of monolithic kernel, if the service is crashed, whole system crashes. In terms of microkernel, to write a microkernel, microcode is required. Whereas in monolithic kernel, less code is required. Some of the examples for micro and macrokernels. OS examples for microkernels are QNX, Symbian, L4 Linux, Singularity, Mac OS X, etc. Examples for macrokernel are Linux, BSDs, OpenBSD, Microsoft Windows, Solaris, OS9, etc. Let us look into task. Task is a job, is an executable program and is independent process. No task can call another task. The OS can only block a running task. It runs when it is scheduled to run by the OS, which gives the control of the CPU on a task request or a message. Example for task is one word file at a time. A process. Process is an instance of a computer program that is being executed. Multiple instances of the same program can execute simultaneously. A process needs various system resources like CPU for executing the process, memory for storing the code corresponding to it, and associated variables, I/O devices for information exchange. It is sequential in execution. As an example, writing of more than one Word file or inserting a picture shape in Word file. Thread. A thread is a primitive that can execute code. A thread is a single sequential flow of control within a process. A process can have many threads of execution. Different threads which are part of a process share the same address space, that is, they share the data memory, code memory, and heap memory area. Threads maintain their own thread status, that is, CPU register values, PC, and stack. Examples for threads are automatic spell check and automatic save of a file while writing a Word file. What are the differences between thread process and task? A program in execution is known as process. A program can have any number of processes. Every process has its own address space. Threads uses address space of process. The difference between a thread and a process is when the CPU switches from one process to another, the current information needs to be saved in process descriptor and load the information of a new process. Switching from one thread to another is simple. A task is simply a set of instructions loaded into the memory. Threads can themselves split into two or more simultaneously running tasks. These are few differences between threads and processes. Thread is a single unit of execution. It does not have its own data memory and heap memory. It shares the data memory and heap memory with other threads of the same process. A thread cannot live independently. It lives within the process. There can be multiple threads in a process. The first thread calls the main function and occupies the start of the stack memory of the process. Whereas process is a program in execution and contains one or more threads. Process has its own code memory, data memory, and stack memory. A process contains at least one thread. There can be multiple processes with multiple threads in each process. Threads within a process share the code, data, and heap memory. Each thread holds separate memory area per stack. There are some more differences between thread and process. Threads are very inexpensive to create, whereas processes are excessive to create. Expensive to create, involves many OS overhead. Context switching is inexpensive and fast, but context switching is complex and involves a lot of OS overhead and is comparatively slower in process. If a thread expires, its stack is reclaimed by the process. But if a process dies, the resources allocated to it are reclaimed by the OS and all the associated threads of the process dies. Some of the standard threads are POSIX threads, Win32 threads, Java threads. Multitasking and multiprocessing. Multiprocessing is the ability to execute multiple processes simultaneously. Systems which are capable of performing multiprocessing are known as multiprocessor systems. Multiprocessor systems possess multiple CPUs and can execute multiple processes simultaneously. Multiprogramming and multitasking. Multiprogramming is the ability of operating system to have multiple programs in memory which are ready for execution. Multitasking is the ability of operating system to hold multiple processes in memory and switch the processor from executing one process to another process is known as multitasking. As an example, opening a Word file simultaneously, you can open a PDF file. While modifying the Word file, you can hear YouTube video. These are multitasking. Context switching. The act of switching CPU among the processes or changing the current execution context is known as context switching. At the time of context switching, the current context of execution will be saved in PCB, that is, process control block, to retrieve it at a later point of time when CPU executes a process which is interrupted currently due to the execution switching. This is the diagram for context switching. In this, process 1 and process 2 are shown. When the process 1 is in the running state, process 2 is in wait state. If the process 1 is in wait state, process 2 is in running state. But before going to running state, for a small time, process 2 will be in the idle state. When the process 1 is running, process 2 will be in the idle state and it is in fact waiting for the running state. When the process 2 is in running state, process 1 goes into idle state. As long as the process 2 is in running state, process 1 is in wait state. Once the control is given to process 1, process 2 push into wait state. Under idle state, execution switches to process 2 and save current context into PCB 0, that is process control block of 0, then perform other voice operations related to context switching, reload context of process 2 from PCB 1, that is process control block 1. Context saving and retrieval. The act of saving the current context which contains the context details such as register details, memory details, system resource usage details, execution details for the current running process at the time of CPU switching is known as context saving. The process of retrieving the saved context details for a process which is going to be executed due to CPU switching is known as context retrieval. Types of multitasking: cooperative multitasking, preemptive multitasking, non-preemptive multitasking are the three types of multitaskings. Cooperative multitasking is any task or process can hold the CPU as much time as it wants. Other processes will be in the waiting state till the current process completed. Preemptive multitasking. The currently running task is preempted to give a chance to other task process to execute. In this case, the preemption takes place with priority. The preemption of task is based on time slots or task process priorities. Non-preemptive multitasking. The task will be allowed to execute until it terminates, that is, completed state or enters to block or wait state, waiting for an IO or system resource. Task scheduling. Determining which task or process is to be executed at a given point of time is known as task process or scheduling. The kernel service application which implements the scheduling algorithm is known as scheduler. Schedulers are also called as dispatchers. Schedulers are part of the kernel responsible for determining which task runs next. Most real-time kernels use priority-based scheduling. Each task is assigned a priority based on its importance. The priority is application specific. When scheduling is supposed to require, the process scheduling requires when a process switches its state to, that is, ready state from running state is nothing but preemptive scheduling. Block state from running state is nothing but priority based scheduling. Ready state from block state, ready state from wait state, then completed state. Preemptive or non-preemptive scheduling, preemptive or non-preemptive and cooperative scheduling. What are the factors behind scheduling algorithms? CPU utilization, throughput, turnaround time, waiting time, response time. A good scheduling algorithm follows these are the factors in such a way that CPU utilization time indicates that how much time the CPU is busy in execution. Throughput is nothing but number of processes executed per unit time. Turnaround time is the amount of time taken for completion of process execution, whereas waiting time is amount of time spent by a process in the ready queue to get the CPU time for execution. Response time is the time elapsed between the submission of process and its first response. In all these cases, a good scheduling algorithm has high CPU utilization, minimum turnaround time, maximum throughput, and least response time. Various queues are followed such that job queues, ready queue, device queue will be used in scheduling algorithms. Types of task scheduling: clock-driven scheduling, preemptive scheduling, in which again preemptive shortest job first scheduling, shortest remaining time, round robin, weighted round robin scheduling, non-preemptive scheduling, in which again first come first served before scheduling, last come first served before scheduling, shortest job first scheduling. Another scheduling is priority based scheduling. For remaining contents, elaborately, you can go to the handouts present in Moodles. So with this, we can wind up Unit 4. Thank you.